Over the last couple of lessons, we've been talking about multiplying polynomials or expanding those expressions. So in the next few days, we're going to be reversing that process, taking a polynomial and breaking it up into its simplest factors. So we're going to start today by looking at a few of those special cases, which should be familiar, as we should have done this in Algebra 1. So the first thing I always want us to look for when we factor is a greatest common factor to pull out. And this is going to be the reverse operation of distribution. So just to kind of jog your memories, in lesson 1.12, and it's not going to be the exact same thing, but I asked you to do something like, I don't know, something like this, which when we wrote it out, looked like this, right? One of the things we said in our previous lesson was we have three things we're multiplying together, and you're allowed to multiply whichever ones you want together first. But we said maybe multiply these together first, and then distribute the two through. The first thing we're going to do when we reverse this process is to take that 2 back out. So maybe I should just change the problem and say, what if we had negative 2 times x squared minus 4x plus 1? So I'm just changing the problem. When we multiplied out, we said, okay, now distribute. Multiply every single term by negative 2. Okay? What we're going to look for today is to reverse this. If you have these three terms, pull that negative 2 back out. Okay? So that's what I want us to look for first. Pull out something that every term has in common. So let's start a little simpler. I have 2x minus 10. That's two terms. Both of them are divisible by 2, which means they must have been multiplied by 2. So we're going to pull that 2 out in front. And when you undistribute, essentially is what I'm doing, instead of multiplying the 2 in, you're going to divide it out. So I'm just going to kind of write that down. I want to divide both of these by 2. 2x divided by 2 is 1x minus, and 10 divided by 2 is 5. So we are undistributing. We are pulling the common factor out in front. And it's important to leave it there. We don't just want to throw it away because, well, it's important. We don't want to change the value of the expression, we're just changing the way it looks. Let's look at the next one. I have negative 9b minus 3. So the first thing I notice is that I can take a 3 out of both of these, and they actually both have a negative. So let's factor out a negative 3, which means we're going to divide by negative 3. Negative 9 divided by negative 3 is positive 3b. Negative 3 divided by negative 3 is positive 1. So we're changing the way the expression looks. We're not changing the value of it. The great news about factoring out a GCF is it's easy to check because you can distribute very quickly and make sure you get right back to where you started. Okay, this one actually looks very similar to this one. Look, the 2 and the minus 10, the 2 and the minus 10. But we can see there's a difference in the variables, right? So the 2 and the 10, oh yeah, both terms have a 2. But I also want you to notice that they both have at least one x in them, which means they have an x in common. So let's take out a 2 and an x. So the 2's are gone. I had x squared, but I took 1 out, so I'm left with just a single x, right? Because x squared means x times x. And let's see, 10 divided by 2 is 5, and x divided by x is 1. So the inside looks exactly the same as this one. It's just that we had an extra x we could pull out. That's pulling out a GCF. Let's take a look at these. So I have a 5a squared plus 5b squared minus 5. So I have 3 terms. And they don't all have variables in them, so I can't pull out any variables, but we see that they all have a 5. And again, if you start with 3 terms, you should still have 3 terms. And I'm saying that for a reason. So when I take out a 5, I'm left with an a squared, a positive b squared, and then a minus 1, right? 5 divided by 5 is 1. So I made a mess with different colors, but I have a 5 times the quantity a squared plus b squared minus 1. One of the most common mistakes I see all the time is for us to just say, oh, 5 divided by 5, and then think it's gone. But it's a 1, right? 5 divided by 5 is 1. So you start with 3 terms. You still need to have 3 terms on the inside. Okay? Let's look at this next one. I have 2 terms. They both are divisible by 2. They both have at least an x, and they both have at least a y. So I'm going to take out a 2 and x and a y, which means I'm going to go in and divide by 2xy divided by 2xy. Great, 8 divided by 2 is 4. X squared divided by x is x, and the y divided by y is 1. So I'm left with a 4x. I've got my minus already written down. The 2's are gone, the x's are gone, the y's are gone, and I'm left with a 1. Okay. Good. I'm going to add one more to this, if I could. Yeah, why not? What if we had something like negative 6x squared plus 12? Okay. So when I look at these, both of them are divisible by 6. And that's actually all they have in common, right? They don't have any variables, both of them don't. So I'd say they both have a 6. However, remember back here when I said let's take out a negative because they both had one? They both don't have a negative. However, I do not love when my first term is negative. So even though they both don't have a negative, I am going to pull out a negative, because you can. Dividing by a negative is just going to change the sign. So negative 6 divided by negative 6 is 1, so I'm left with an x squared. A positive 12 divided by a negative 6 is a minus 2, or a negative 2. So I just wanted to end with that, because even though they're both not negative, you can still pull out a negative. You can factor out a negative anytime you want. And I am always going to do that when my leading coefficient is negative. Okay? All right. So the other thing I want us to start looking for is actually reversing something that we did in our previous lesson, lesson 12. We did this on, well, we did on Friday in lesson 112. And we said when you multiply conjugates, remember that's what these are called. Conjugates are binomials that are identical except for the sign in the middle. And so when we multiplied those together, I FOILed, right? And we had a times a, which is a squared. We had a negative times a positive, so a negative, and a times b. Went to the inside, we got a positive a times b. And then when we did the end, we got a negative times a positive b squared. And so when we multiplied conjugates, the outside and the inside always went away. So we said you actually don't need to FOIL, you just need to do the firsts and the lasts. And that got us to a squared minus b squared. So again, this is just what we were doing on our previous lesson. So I'm going to write this down. A plus b, actually I'm just going to reverse it, doesn't matter. I'm going to say a squared minus b squared is equal to a plus b times a minus b. Because if we're reversing what we were doing on Friday, instead of saying let's multiply conjugates to get this, we're saying what if we have this? If you have two perfect squares with subtraction between them, a difference, remember difference means subtraction. So if you have a difference of two perfect squares, that will factor into two binomials. They'll be conjugates. You're going to take the square root of a squared, and you get a. You're going to take the square root of b squared to get b, and you put a plus or minus between them. Okay? All right, so let's take a look at these right here. So I have x squared minus 16. Oh, that's a perfect square. That's a perfect square, which means I should be able to factor it into two binomials. The square root of x squared is x. The square root of 16 is 4. we put a plus between them, we put a minus between them. And that should be factored. Remember, when we factor something, we're trying to turn it into multiplication. So instead of this minus this, I now have something times something. That's our goal. Okay. Let's look at the next one. I have two terms, subtraction, there's that difference, and I'm asking, are they perfect squares? That's squared, and 144 is 12 squared. So that's a difference of squares. The square root of n squared and the square root of 144 is 12. We put a plus between them, we put a minus between them. Now, the best thing about factoring is that you can check by multiplying it out. I'm not going to, but you can do, FOIL and see that you get right back to here. All right, let's take a look at the next one. I have two terms with subtraction between them, and these are perfect squares. The square root of 4 is 2, the square root of h squared is h. The square root of 49 is 7, and the square root of k squared is k. So I've got a 7k at the end. We put a plus between them, we put a minus between them. We are changing the way it looks without changing the value of the expression. All right, let's take a look at this next one. So I have negative, I have subtraction, but then I go, oh, that's not a perfect square. Well, don't forget that the very first thing you should look for is a greatest common factor. So I think, oh, look at that. Both of these are divisible by 2. And when you take out a 2, you're left with 25 minus x squared. And that is a difference of squares. So again, don't lose that 2. It has to stay there. But then I can take the square root of 25. I can take the square root of x, and I can put a plus and a minus between them. While I'm talking about this, and I should have said it before, the order does not matter, right? If I put the minus here and the plus here, that's not going to change a thing. When you multiply, the order in which you multiply doesn't matter. The order of the things inside does, but the order of these parentheses does not. Okay, for instance, let me just go back to a simpler one. You could have had x minus 4 times x plus 4, and it's the exact same thing. The order of the binomials doesn't matter. The order of what's inside does. Okay. Now, let's take a look at this next one. All right, so I have, again, we're still asking to factor. I have negative 5x squared plus 45. First of all, I notice that it's not a difference of perfect squares. What I do notice is that they both have a 5 in them. In fact, one of the things I said earlier is if the first term is negative, I'll probably take the negative out with it. So I'm going to pull out a negative 5, which leaves me with an x squared minus, right? A positive divided by a negative is negative, 9. I'm going to do this problem two different ways. I'll come back to it and do it in a second when it says or. So I said, let's pull out a negative 5. Great. Now that I did that, I see that difference of squares, and I can factor and do an xx, 3 plus minus. Okay. Another option would be to just factor out the 5, right? You can factor out a 5, but you'd be left with negative x squared plus 9. And you're right, that's still not a difference of squares. However, if you trade places, now you say, oh, look at that. It's a difference of 2 perfect squares. So the square root of 9 is 3, the square root of x squared is x, and you've got a plus or minus. So the answer looks different. It should. But it's not different, right? This one has a negative 5 out front. This has a positive 5, which is what makes it look slightly different on the inside. Not bad, just different, okay? All right, let's take a look at the last one. So I have two terms with subtraction between them. However, that's not a perfect square. This is not. But do not forget to pull out a GCF first. They both have at least 2 x's, so they both have x squared in them. which means I'm going to divide both of these by x squared, which leaves me with an x to the first minus 16. This is no longer a difference of squares. This does not say x squared. This is just a linear factor. It says x to the first. So I don't need to worry about that one anymore. It's done. Sometimes just pulling out a GCF factors it completely.